that. Yes, Chrome, let's see what happens. Hey, it's working. Maybe. Okay. Why do we just see the giant mirror casting? This is so funny. Like this morning, it's totally no problem. And then your class starts and it's like, no, I don't want to do it. No one wants to learn chemistry. I get it. But we don't have a choice. Ho ho. Still no, what the heck? Well, while we encounter these technical fun things, does anybody have any questions about stuff from last time? Yep, exactly. And God's like, forget it. You're not doing... Aha! No more sig figs for you. But looks like no such luck for us. Alrighty, so we are unfortunately fully functioning again. So here we go. Let's continue with some fun stuff. Let's do some multi-unit conversions here. So last time we did one where we had like, what was it, like feet squared in I don't know, we started with inches or something, I don't remember. But we can do it with multiple units that aren't the same thing as well. So let's say we are all good people who go 65 miles per hour, right, on the freeway, because we obey the laws. And so let's say I want that in meters per second. We can calculate this. So notice that we have a distance over a time unit, and we are converting to a different distance over a different time unit. So let's throw out a bunch of conversion factors for us here. I will say that we have the 3.27 feet equals 1 meter, 50 to 80 feet equals 1 mile, and let's see, 60 seconds equals a minute, and 60 minutes equals an hour. Alrighty. So we can totally do this. So lucky for us, I've given us 4 conversion factors. That's kind of a hint there. But if we just look at what we're starting with, we have miles per hour, and we want to end up with meters per second, right? So we can kind of plan out what our dimensional analysis is going to look like by doing what's called the unit plan, right? So we can either mess with the distance unit first, or we can mess with the time unit first. It really does not matter. I typically like to do the numerator first just because, I don't know, it's just preference, I guess. Again, you could mess with the denominator first, does not matter. So if we want to do the numerator first, we can do that. So looking at these, we want to get from miles to meters, right? And so we only have one conversion factor that has miles in it. So that's the one we're going to have to use, right? And that's going to end up giving us converting it from miles into feet. So our unit's going to be feet per hour then. From there, we see that we have a conversion between feet and meters, so we can use that. And so now we will have kind of the numerator done. We just now have to work with the denominator unit. And so from hours to seconds, yes, I mean, we could say 3,600, but for fun, let's pretend we don't know that. And we're going to want to convert to minutes first. And then finally from minutes into seconds. So nice and logical kind of plan here, systematic step by step. We are going to notice that we have 1, 2, 3, 4 conversions that we're doing in this problem. And luckily for us, we have 4 conversion factors as well. So when you're doing these sort of plans like this, just to help you to organize your thoughts, you can see exactly how many conversion factors you're going to need by looking at how many like arrows you've got in your plan. So let's do it. Let's take our 65 miles per hour and see what we're going to do. And since we know we're doing 4 conversions, that's going to give us 4 fractions, right? And then we're going to have our answer. So the first one we saw in our plan was we're going to go from miles to feet. So we're going to look up which conversion factor, of course, has miles to feet. That's this one. Looks like we have miles in the numerator here, so we're going to want to put 1 mile in the denominator so they cancel out. And we're going to put our 5280 feet. I hope that's the right number. Does that sound right to you guys? I can never remember the US units, even though I've spent 30 years dealing with them. I hope that's right. Well, it doesn't really matter. We don't have to be super accurate with this problem, so cool. Our second one, we were going from feet to meters. So we're going to see, okay, we're going to use our conversion from feet to meters. Feet is going to go on the bottom. 1 meter. Again, just make sure that when you're using conversion factors, we want to keep the numbers with the unit that they're given with. So 3.27 went with feet, so 3.27 went with feet in our fraction as well. All right, so now we're messing with our time units. So if we just kind of pause, we see right now we are in units of meters per hour, right? So we have hours in the denominator. If we want to get rid of that, we're going to have to put hours in the numerator. And therefore, we're going to put minutes in the denominator. And then same thing here, we're going to put minute there, and then seconds in the denominator. Looking at all of those, hours will cancel, minutes will cancel. Note we're left with, I guess that should just be an S, not seconds like that. I'll use the real abbreviation. So we have the units that we want to end up with. And so now all we have to do is multiply across, divide across the bottom, and we go to Google to do this for us. Or not, because it doesn't want to work. So we bust out our phones, and we're going to do the math here. Or if someone wants to do it for me, that'd always be appreciated. 5280 divided by 3.27 divided by 60 divided by 60. Okay, so I got 29.1539 blah, 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 blah. And so Kevin has already done our sig figs for us, as always. Class superstar there. Let's just take a look at what things we have to worry about with sig figs with this problem. Of course, we have a measured quantity, our very first one, so we should always consider that. We don't have to worry about this sig figs because that's a same system conversion. That's a defined thing. If a mile is defined as 5280 feet. Here we will have to pay attention to the 3.27 because we are changing in between systems. And then if we look here, the 60s don't matter because those are defined quantities as well. So we know 60 seconds is a minute and 60 minutes is an hour. Those are defined. So looking at that, we have 2 sig figs and 3 sig figs. Remember, we never want to worry about the 1. And so our answer should have 2 sig figs, so we're going to round it to 29 meters per second. Okay, and notice Kevin's answer has included the unit also. That's, of course, very important because in, elementary school or whatever, you were yelled at for, not writing your units a million times. So hopefully you guys still have that habit. So definitely write your units. Alrighty, and so you can always double check that you have this done correctly. If you're canceling out your units properly, make sure things cancel out when they need to, and make sure you end up with what you need to. And remember, multiplication division you can do in any order you want. So if you wanted to do the time part first instead of the distance part, you could have done that. Totally no problem. You could have put those 60s towards the front of the dimensional analysis. There's no problem there. Cool. Any questions on that while I start writing our next one? Let's see, how nasty shall I make this? That's the real question. Okay. How about we do... Okay. How about we say 362 liters per... No, not that. Kilometers per liter. Yes, that'll work. And I want this in cubic feet. What shall we do? How about yards? Because I am a, sadistic chemistry instructor, so I want to make things stupidly hard for us. But we can do it. Again, this is a proof of concept, making sure that you understand the process here. Because in fact, you're pretty much never going to need to memorize formulas in chemistry if you know how to do this. If you can mess with your units and know what your conversion factors are, you're always going to be gold. So, let's see. I'll give you some conversion factors here. So again, we have that 3.27 feet is 1 meter. I will tell you that 1,000 liters is a cubic meter. We of course have our metric one here, and then we have 3 feet equals 1 yard. Yeah, that'll work. Okay, so that should be all of the things that we need here. So we're gonna go ahead and do it. So there's only one thing. Wait, why did I have... Oh, no, that works. Okay. Yeah, this will work. Okay, cool. This is going to be pretty nasty, guys, so we'll get through it. So, kilometers per liter. We want to end up with yard per cubic feet. All right, you might be like, what the heck? We went from a cubed unit or non-cubed unit to a cubed unit. Remember, liters is volume, so is cubic feet. They're representing the same quantity. So we're okay there. So I always like to do the top one first, but again, does not matter. You can do it whatever order you want. So if we're planning this out, we're going to probably go to meters per liter. And then from meters per liter to feet per liter. And then to yards. I think YD is... that. So now we can mess with the bottom one. We are going to have to convert from liters to meters cubed, and then we'll have one from meters cubed to feet cubed. So longer conversion, we are going to have 1, 2, 3, 4, 5 conversions this time. Note that I only gave you 4 conversion factors, but we'll be okay. We're going to, in fact, use one of them multiple times. Hooray! Alrighty. So notice here also we have cubed unit to cube unit. Right? That one is the only one that's going to be tricky for us, right? The rest of them we can just use as is. But for this one... we're going to probably want to remember from last time that we can cube both sides of this, right? And that way we will get a conversion factor between feet cubed and meters cubed. All right, so, or we could do it 3 times, but we are already going to be low on space with 5 fractions here, so let's not go too crazy. Alrighty, what did we have? 362. Okay. Let's do it. 2, 3, 4, 5. Alrighty, so kilometers to meters. We're going to be using that third conversion there. Kilometers on the bottom. Meters on top. We're going to want to do feet on top, meters on bottom. And then 1 yard to 3 feet. And then notice here we're going to, that we have 1,000 liters. I'm just going to put 10 to the 3 liters just for saving space. Is going to be 1 cubic meter. So notice that we're going to have liters canceling out. So we have put the liters on the numerator. And our last one, we're going to have to put the cubic meter with the 3.27 cubed down there. I'm sure Kevin has already done the work for us. And I hope so, because I don't want to have to punch in this crap to the calculator. So let's see. Fine, I'll do it. Okay, here we go. 362 times 1,000 times another 1,000 divided by 3, divided by 3.27, divided by 3.27. Wow, this is huge. Cool. Okay, I got this really big number, which is crazy. So I got 11,284,746.57. Something absurdly large. Again, I'm totally making up this number, 362 kilometers per liter. Like, that's a Prius on steroids, on steroids, on steroids. I think that's a pretty crazy amount of fuel efficiency there. But yeah, here we go. Okay, so let's see. By the way, let's make sure our units canceled out before we accept this crazy number. Did we have kilometers canceling out? Yes, we did. Did we have meters canceling? We did. Feet canceling? We did. Liters canceling? And cubic meters canceling. That's awesome. Notice, because we have 3.27 on the top and on the bottom, we could have just simplified our calculation there, but let's not worry about that. So we'll multiply everything on the bottom, divide everything, multiply everything on the top, divide everything on the bottom. Hopefully I've done that correctly in my calculator. Kevin will let me know otherwise. Looking at our conversions here, we have to look at sig figs in 3 places. And it looks like all of these have 3. So we're going to round our number to 3 sig figs. So we're going to round based on the 8. So that's going to be 113, 0, 0, 0, 0, 0. What was this? Yards per cubic feet. Okay, or in scientific notation, you could do that. 1, 2, 3, 4, 5, 6, 7. Same thing. Awesome. So if Kevin got it right, that means I got it right too. So that's awesome. We have done our math properly. Got some crazy, absurd number. Yeah. Of course. Feet cubed. Great job. Alrighty. So we can do this with cubic units, with squared units, with whatever. The important thing is that we make sure our units cancel out. And we're putting them on the right side of the fraction. So either the numerator or denominator. So, any questions with that? Okay, so there's one more conversion factor that I want to talk about with you guys. It's a special one. Which is density. Okay, because of the infinite wisdom of the physicists, this is abbreviated with the Greek letter rho, not a D, unfortunately, even though that would make sense for us. And density gives us the conversion between mass and volume. All right, so it is a conversion factor. In math or whatever, you might have seen it as a fraction, mass over volume. But remember that fractions are the same things as conversion factors, right? They are identical. So, an example of a density might be, for example, ethanol has a density of 0.789 grams per milliliter. This is a conversion factor. So we could use it also as 1 ml over 0.789 grams, right? We could use it either way, just like any other conversion factor based on what we're given. So we could start with grams and end up with mLs, or we could start with mLs and end up with grams. Either way here, does not matter. So you'll see this a lot, presumably. It's just another conversion factor. You may be required to calculate your own conversion factors, which is okay too, because if we say, I don't know, I'm just going to make up random substance. Let's say that it is 30 grams is equal to 11.6 mLs or whatever. We can come up with the conversion factor that's going to get us there. So typically we put 1 with ml. That's just how we represent density standard. And we could figure out what number should go in here, right? We can just algebraically solve this and you would come up with the density, right? No, this is not an exact one because we would have to have measured this. Water is not exact either. So density, very good point. Thank you for mentioning that. Let's put this in purple. And so typically this is a lab experiment that you guys would do probably many times throughout your chemistry career. It's a pretty standard thing to do. And you would be able to figure this out, right? You would put something on a scale. It would give you, okay, this is 30 grams. And depending on this volume, you would either, if it was like a cube or something, you could measure the sides and use geometry to find the volume. Or if it's a weird shaped thing, you could use calculus, but why? An easier way is you just submerge it in liquid. And so, if you guys have a bathtub that's completely full of water and you get into it, the water is going to spill out everywhere, right? Because you will displace that water as you get in. And so, same thing here. If you have a known volume of liquid in some sort of container that could measure volume, you put your object in, the water level will rise, and you can see the difference between those will be your volume. So typically a very standard thing, and you would calculate the density doing this. So algebra, let's do it. Here, let's throw in an X because we like variables, right? Instead of question marks. Oops, sorry. So, we could say, hopefully you know how to do this algebraically, right? We would presumably multiply both sides by X. We would get 30 grams equals 11.6 times X. mLs will have canceled out. Or rather, they would not because, well, fine. Let's just forget the units right here. Let's do the algebra. We know our units already, right? And so Kevin's already done it for us. He's gotten 2.59 grams per ml, and that will be the density for this particular thing that we measured. Okay, and he's already applied sig figs. Both of those numbers had 3 sig figs, so we will have 3 sig figs in our answer. Okay? So you can solve for conversion factors too. So even if on this monstrosity of a problem up here, if I didn't give you this conversion factor or something, and I gave you the answer, the 1.13 times 10 to the 7, you could solve for that conversion factor, right? It's just algebra. Nothing crazy there. So one variable, just a bunch of numbers, plug it in, plug and chug, you get your answer. Okay, so I will be giving you more homework because you clearly don't have enough. And so you will see density as something you will need to use as a conversion factor. Okay? The last thing I want to talk about is just units in general. So if there are no questions on unit conversions, we'll just talk about units in general. Common units. Okay, so we have some common measurements in chemistry. We have energy. Let's see, we have mass. Here, we can work with these right now. So common units for length. Of course, the standard unit for us is going to be the meter. But, we, of course, in the infinite wisdom of the US system, we have all these other random units that don't make any sense. Some guy's foot happened to be 12 inches, and that was standardized for some reason, and, we're stuck with that. For volume, we typically use liters or cubic meters. Typically, cubic meters is the standard one, but liters is probably more common. In the US system, we have gallons, ounces, rather fluid ounces, because let's name everything the same. And we have, let's see what else. We have, cups and quarts and all that random stuff, random units like that. For temperature, thankfully, we only really use 3 of them. Celsius, Fahrenheit, and Kelvin. Fahrenheit's kind of awful. We'll never be using that in chemistry. You've done Fahrenheit to Celsius conversion in, elementary school or whatever. You don't need to do that again here. I don't really care about that. That's a very just plug and chug into the formula. However, Celsius to Kelvin will be an important one. We will discuss that below. So I'll just put a little star by it to remind myself. Units of energy. Typically we'll be using joules. Actually, that does not have a capital J, which is abbreviated capital J. Or calories, which are cals. Thankfully, we don't do too much with US with these, so calories are pretty standard as well. And then for mass, we have, kilograms is kind of our standard, therefore grams, milligrams as well. For us, it's going to be pounds in US units, or ounces, or grains, or stones, or whatever other random units that we have come up with that don't make any sense. You have 16 ounces to a pound and 14 pounds to a stone. It's like these things just make no sense. So, forget it. We won't be using this as much. For our temperature one, we have a happy formula, which you will want to learn. Notice Kelvin does not have no degrees, because it is absolute. Absolute meaning can't be negative. You can totally have negative Celsius, not a problem. Your fridge is set to about your freezer is about negative 20 Celsius. That's pretty standard. You can have Celsius that's negative. You can have Fahrenheit that's negative, no problem. But Kelvin can never be negative. Kelvin, Actually, if you have 0 Kelvin, that's the moment at which all movement stops. Things cease to do anything. There's absolutely no kinetic energy in your system. It's not really possible to reach that as of now, but we can get pretty close. But can never be negative. Okay, you can't have negative Kelvin. Okay. Celsius, by the way, the other word we would say is relative. That's a relative scale. Okay, one thing to note about these, you can multiply absolute scales. You can say, okay, 10 Kelvin versus 20 Kelvin, that's twice as hot. Right? But if you say 10 degrees versus 20 degrees Celsius, that's not twice as hot. So even though that's a 10 degree difference, right? It's a measured quantity. It's not a conversion factor for temperature. So there's no worries there. You would worry about sig figs with the 273.15. So if your temperature, typically temperature, like thermometers don't read that many sig figs, so you probably would be okay. But it's just typically a measured quantity. Notice also that I could go from 0 C versus 10 degrees C. It's still a 10 degrees difference, but it's infinitely times hotter if you were to say that. It doesn't work that way, right? Or, like negative 10 versus, or let's say negative 20 versus negative 10 degrees Celsius. Like, another 10 degrees difference, but, like, it's not twice as hot, right? Can't say that. Cannot multiply our relative scales. But absolute scales we can. We can say for sure 10 Kelvin is half as hot as 20 Kelvin. All right, so that's how it's going to work. Okay, none of these Celsius ones, or if we were to do Fahrenheit, would work. So we can't say 50 degrees Fahrenheit is half as hot as 100 degrees Fahrenheit. It does not work that way. Okay, because that's a relative scale. Okay. Any questions on units, by the way? The last thing I want to talk about in this chapter is going to be how to use that handy-dandy metric system chart that I gave you guys. So, in Discord, I posted it for you. It had a bunch of prefixes and exponents, right? What we want to do with this is we're always going to say 10 to the x base unit. The x is just going to come from that chart, will be equal to 1 of your prefix unit. What I mean by that is we could say something like this. If we were to look up kilo on the chart, we would see that kilo has, let me see, let me just open the thing up. Forget it, I can't right now. Oh wait, yes I can. Because we have Discord right here, duh. Okay. I lied, it's not in this channel. Extra resources, where the heck did I put, oh there it is, yeah. Okay, so here's our handy dandy chart, right? We look up kilo, we see it says 10 to the third. So we are going to put 10 to the third with our base unit, which was this guy, and we're going to put 1 with our prefix unit. We could also say, oops, I just messed that up, didn't I? We always want to put it with the base unit. 10 to the 6th grams equals 1 megagram. We could also say 10 to the negative 9th grams equals 1 nanogram. Okay, these are just exponents I've gotten from the chart. Okay, I could also say, 10 to the negative 6th liters is 1 microliter. Okay, so that's how we're going to be using these. So if you ever need to come up with conversion factors for the metric system stuff, you'll do it this way. If you know how to do it another way, you're totally welcome to. Some people prefer to only use positive exponents. You're totally welcome to do with that. Like, for example, technically you can say 1 gram equals 10 to the ninth nanograms, right? That's mathematically correct. But for consistency, I just like to do it just the way that I've written here. You're, of course, always welcome to use whatever way you like. So, okay? Any questions on this? I wonder if Oz is far enough away. Can you guys hear him barking right now? Or rather, grumbling? Yeah, you can. Okay, well, you get to deal with it. We only have 20 more minutes, so you can survive. Well, now he's stopped anyway. Maybe he's going to go take his nap now. So, okay, cool. So, if there are no more questions, we will move on to our next topic, which is atoms. Hooray! So, I don't really like explaining the history of like how we know atoms exist and all that stuff. I think it's kind of like, yeah, it's great that these people 200 years ago did these experiments and they found these things out, but like that doesn't really improve our understanding nowadays, right? We know atoms, I mean, it's pretty common knowledge, are made of 3 things, right? Protons, neutrons, and electrons, right? If you want to learn the history of it, you go right ahead, look at the textbook. The first section of chapter 2 talks about how we learned about these things' existence, but you can learn history on your own. Cool. So, but now, you know, you learn in middle school or elementary school that atoms are made of protons, neutrons, and electrons, right? And so we're going to see that all of these things are going to have a charge, and a mass, and a kind of location. Location. Let's fix that. Location. So protons, we know, will have a positive charge. Electrons have a negative charge, and neutrons have 0, of course. Technically, this charge is 1.602 times 10 to the negative 19th coulombs. You don't need to memorize that. But like when we say +1 charge, in terms of like actual units, that's the charge there. So it's positive 1.602 times 10 to the negative 19 coulombs. Electrons is just negative of that. Okay, the mass of a proton is about 1 atomic mass unit. Same thing with a neutron. An electron is about 1 over 2,000 atomic mass units. So protons and neutrons are roughly equivalent in mass, and electrons are going to be much, much smaller. So we're going to see very often we kind of just omit electron mass because it's just insignificant compared to the mass of the protons and neutrons. And we also know that protons and neutrons are in the nucleus, which I can't spell correctly. And electrons are kind of orbiting the nucleus. Okay, so hopefully none of this is new information. Pretty standard stuff, right? And we're going to see that we can mess with all of these things. I'm going to give you a couple of examples here. So let me first display how we're going to talk about individual atoms. So this is a typical way of describing an atom, where we are going to have... Actually, I'm going to just move that a little bit. Let's see. Can I actually do that easily? Let's see. Oh, how cool. Okay. Look, teachers can use technology too. Okay. Cool. A here is going to be the mass number. That's going to equal the number of protons plus the number of neutrons. Okay, Z here is known as the atomic number, which is equal to the, technically it's equal to the charge of the nucleus, but let's just say right now it's number of protons. Okay, and then E here is the element symbol. And that's going to be on the periodic table. Very often it will either be, actually not even very often, always, it will either one capital letter or one cap plus one lowercase. For example, you could have carbon, you could have cobalt, you could have sodium, you could have potassium, right? So element symbols are either one letter and is capitalized, or they're two letters with the first one capitalized. Okay, notice that that is not the same thing as that. We are going to learn cobalt is on the left, and on the right side of that one is carbon monoxide. So those are totally different. So it may be a good idea to kind of exaggerate your lowercase, make it like a really small comparatively. Okay, so let me give you a couple things. So also here, we don't have it written, but often we'll have the overall charge written here if it's not 0. So let me give you a couple of examples. Let's just get rid of this cobalt is not the same as carbon monoxide. And I'm going to get rid of these things. For example, we could say, I would actually need my periodic table for this. Actually, no, I remember. It's magnesium, if I remember correctly. Okay, so we're going to see, this is an example of magnesium. Okay, so we're talking about magnesium atoms here. We're going to notice a couple of things about this. So notice that if we look at these, and so typically we don't write a charge if it's 0, but I'm going to just write the charge here just to make it super obvious for us. So if we look at this, we can try to kind of see that the number of protons, number of neutrons, and number of electrons for these guys. We can see that these magnesiums all have 12 protons. Remember, the number on the bottom is equal to the number of protons, right? The Z part of that is the number of protons. Remember that the number on top, the A, is the mass number. That's the number of protons plus the number of neutrons. So, because this one is equal to P plus N, we can subtract P from both sides, right, to figure out what N is. And so in this case, we're going to have 12 neutrons here, 13 neutrons here, 14 neutrons here. All right, so number of protons in this case is all the same. So each kind of time we're increasing this, we're just adding more neutrons. Alrighty, and now let's think about the number of electrons. So this one is not as obvious to us. However, we can see that the overall charge is 0, right? And that tells us that if the overall charge is 0, that the number of electrons must be equal to the number of protons. Remember, they're opposite charge. Proton is positive 1 charge, and electron is negative 1 charge. So if we have overall 0, the numbers have to be the same, right? So 12 minus 12 equals 0. So we can come up with that. So the charge is the number of protons minus the number of electrons. So that's another one that we can come up with. So because the charge is equal in all of these, we can see that the number of electrons is going to be the same in all of these as well. So, what we notice here is that atoms with different mass numbers are called isotopes. So these three things are isotopes of magnesium, we would say. These three are different isotopes of magnesium. Often we would abbreviate this. We could write out the whole thing, of course, with all the AZE, but we could write it just by saying Mg24 or Mg25 with a hyphen. People will write it this way. We will talk about isotopes like this sometimes. Some people will also write it just, 24. Yikes, that was the hideous 24. You could also have it written this way. People will just omit the 12 there. So this is how people talk about isotopes. And we would read this as magnesium 24. Like if you were to read this aloud, you would read it as magnesium 24. You would read the next one as magnesium 25 and magnesium 26. That's how we'd talk about isotopes. So looking back at these, what have we changed between these atoms to distinguish them as isotopes? What's different about these guys? Yeah, exactly. So the number of neutrons is different, and therefore the mass number is going to be different, right? So if we have atoms with different numbers of neutrons are isotopes. Okay? So as a result, the mass number is going to be different, but in terms of these subatomic particles, we're going to see that the neutrons are going to be what distinguishes isotopes from each other. So it's the same type of atom, but they have different numbers of neutrons. Okay? Hopefully so far so good. Let me give you another example. Is it scandium that's next? I think so. Correct me if I'm wrong there. But we can do the same thing here. Or do I want to leave them this way? I'm gonna change these a little bit. Yeah, that should be okay. Okay, we'll deal with it this way. So I'm going to say that these guys are different elements. We can tell that right away because they have different symbols, right? Each element has its own symbol. And so we can see that these, because they have different symbols, are different elements. But let's go ahead and look more closely. Protons, neutrons, electrons. Let's do it. Easiest one to do is protons, because that's just the number on the bottom. Oh, it's 21. What's after magnesium then? Oh, it's aluminum. Duh. There are no transition metals that easily. Thank you. Sorry about that, guys. And girls, of course. And non-binary. Okay, looking at the number of neutrons, in this case it's going to be 24 minus 11. That's 13. Sorry, I will be consistent as well. I will use blue. For this particular magnesium atom, it is also 13, and I've been consistent. We're going to have 13 in our aluminum as well. Alrighty, and so looking at this, because all these are uncharged, we can say, okay, look, this has 11 electrons, 12 electrons, 13 electrons. So far, we understand that different elements have different numbers of protons or electrons. So far. We are going to come back and adjust this a little bit. But for right now, according to the data that we have, we can observe that it's the number of protons or electrons which determines the element. Okay. And now let me do one more for you. Oops. Why does that always happen? Magnesium. Shame on me. Okay, in chemistry we like to be bizarre and we write 3+, which means +3. The way it works, sorry. Nothing I can do about that. And if we analyze these, right, we're going to see if we do all this math. Notice that, remember, the charge was protons minus electrons, right? So if your charge was +1 and you had 11 protons, we would, have to add x to both sides, and we would see that x equals 10. Or if your charge was +2, it would be, for example, this magnesium started off with 12 protons, and again, we're going to end up with 10 electrons. Okay, so that's how I've come up with those numbers. So looking at this, even though the same number of electrons is consistent among these particular examples, the number of protons is changing as well as the elements. So we're going to go ahead and say for sure that these guys could have the same number of electrons, but what's going to change there is the charge. So we're going to see that the number of electrons, sorry, let me just write E, determines the charge. So, kind of in conclusions, these determine, your proton determines your element, how many protons you have. Your neutrons will determine which isotope you are of a particular element. And your number of electrons will dictate your charge. And if it's charged, it could be either neutral, if charge is 0, or an ion. Okay, an ion can be either a cation or an anion. Cations are going to be positive, and anions are going to be negative. So just vocab today. So we've talked about our kind of subatomic particles a little bit. Number of protons determines which element you are. Your number of neutrons determines which isotope you are of an element. And your number of electrons will determine if you are charged or not. If you are not charged, you are a neutral element. If you are charged, you are an ion. If you are positively charged, you are a cation. And if you are negatively charged, you are an anion. Okay, So today we are going to leave it there, and we will continue talking about these atoms tomorrow. Okay? So if you guys have any questions on the stuff we've done today, throw them in Discord as always. I'll post these videos up on YouTube, just like always as before. Okay, so see you guys tomorrow. Enjoy the rest of your day.